what we will do is we'll finish the unit today on absorption and air stripping. I have posted 2 videos from Wednesday and Friday. Wednesday's video really focuses on the theory of absorption along with an example problem on aeration of a pond, mechanical aeration. And Friday's lecture focuses on actually DO sag curves, Schrader-Phelps equations, includes some material from the FE reference handbook. So I'm not going to spend a lot of time on the theory today, although I'm happy to answer any questions you have. The theory, as I've mentioned, I've presented and is recorded online. But just to reiterate and kind of get us thinking about the whole process of absorption. We had talked previously about adsorption. There we were looking at the attachment of molecules to a solid surface. And we talked about that solid surface could be anything from granular activated carbon, powdered activated carbon. It can include activated alumina. It can also be fabric. So clothing, curtains, upholstery. Here we're talking about absorption. So we're looking at, this is really, think of it as a 3-dimensional process, and we're looking at moving a chemical, transferring a chemical from a gas to a liquid or from a liquid to a gas. And in environmental engineering, we typically focus on the liquid being water. So as I've mentioned, and I've got more details in the previous lectures, but we can talk about aeration systems. So we can look at oxidation of iron. We can look at aeration systems and wastewater treatment. So we're looking at making sure that we have sufficient oxygen for microbial activity. We can also look at aeration of the effluent before discharge to a water treatment or water body, so that we're making sure that we're not depleting oxygen when the effluent and the water mixes. And we can talk about dissolution of chlorine gas. So we're adding chlorine gas to the water to be treated. If you recall, when we add chlorine gas, that chlorine gas dissolves, forms hypochlorous acid or hypochlorite, depending on the pH. And that is what we use as a disinfectant. Now we can also transfer a chemical from the liquid to the air. So for instance, in a hazardous waste site remediation, we may have groundwater that's contaminated with volatile chemicals like benzene, trichloroethylene, tetrachloroethylene, dry cleaning solvents. Well, we can transfer those chemicals from the liquid phase to the gas phase. Now, why would we want to do that? Well, in some cases, the treatment is more efficient in the gas phase than it is in the liquid. So for instance, we can use catalytic oxidation of those chemicals once they're in the gas phase, and that's more effective, more efficient than if we try and accomplish catalytic oxidation in the aqueous phase. And we can strip CO2 from groundwater. We mentioned this when we looked at lime soda ash softening, how that first reaction in the lime soda ash softening is the neutralization of the CO2. Well, that consumes lime, produces calcium carbonate sludge, and we want to minimize both the cost of chemicals and the cost of treatment and disposal of the residual. So we can strip that CO2. And we'll look at an example like that today. So again, remember that everything with absorption, we're looking at transferring a chemical. So in this case, it's shown as SO2. So for instance, combustion gas has SO2 in it. We may want to remove that. In fact, we often want to remove that from the gas stream before we discharge it to the atmosphere. So we can strip that SO2 from the gas. We can neutralize it actually, because you see we produce sulfurous acid. So we can actually add lime to the liquid to neutralize that acid. But we're looking at the transfer of that chemical from the gas phase to the liquid phase. Now this is an equilibrium process, so there is some movement back. So we need to think about that as an equilibrium process. Now it's very much dependent on this gas film. So you probably can imagine, the greater the surface area of this gas film, the greater the mass transfer. So we want to minimize, for instance, in this case, the water droplets. So we're looking at moving it from the gas to the liquid. We want to minimize the droplet size so we can maximize the surface area to volume ratio. We also have what is referred to as a gas film and a liquid film. Gas film is much thinner than the liquid film, and we need to think about how those impact mass transfer. Okay. Again, I go through a lot more detail in the previous lecture. So in order to get this transfer, we need to ensure that the chemical diffuses from the bulk liquid, from the bulk gas through the interface and then into the bulk liquid. So we're looking, I've written this here as gas to liquid. And all of this is designed based on Fick's law and Henry's law. And we'll talk briefly about both of those. So when we talk about Fick's law, okay, we're looking at the rate of transfer. So we'll write this down as the rate of transfer is a function of the difference between the equilibrium concentration and the actual concentration. So what's shown here is, we could think about this in terms of oxygen. So for instance, let's say we have a oxygen concentration, we'll refer to it as CT, of 2 milligrams per liter. And the saturation concentration at temperature of the water is, let's say, 8 milligrams per liter. So in that case, okay, the transfer is going to be from the gas into the liquid. So we're able to essentially think of it as it's a positive. We've got 8 minus 2, that's positive. So the way we've written this, we've got transfer from the gas to the liquid. On the other hand, let's say we have the same saturation concentration of 8 milligrams per liter. We have a situation where we have significant algae bloom. It's during the day, there's algae are photosynthesizing, and we measure the concentration in the water at 12 milligrams per liter. Now, the direction of transfer is going to be from the liquid to the gas. We've exceeded the solubility. And this figure essentially shows us the same thing. However, what shown here is this interface, and the concentrations at the interface. What we are assuming here, okay, and this whole approach that we're using assumes that the concentration of your chemical in the aqueous phase is proportional to the partial pressure, and I wrote this as, leave this as O2. So for instance, the concentration of oxygen in the aqueous phase is a function of the partial pressure of oxygen. And this is Henry's constant. And this is true for dilute solutions. Okay. Same thing. We can use this for CO2. We can use this for benzene. We can use this for any chemical found at low concentrations, which is typically what we observe in the environment and in most engineering systems that we encounter in environmental engineering. So the absorption efficiency is going to be dependent on a number of factors. These include the liquid ratio of the liquid flow rate to the gas flow rate, and that really asymptotes. So for instance, if we're looking at removing a chemical from the liquid, and we're looking at, let's say, a situation where we have groundwater contaminated with trichloroethylene, as I'm writing. So let's write this as the gas to the liquid. Okay, so we're treating a constant liquid flow rate. That liquid has TCE in it. The water is contaminated with TCE. And I'll plot this versus efficiency. What you see is a plot that looks essentially like this. We can increase the flow rate of gas to a point, but we really get to a point where we reach diminishing returns. We're increasing our flow rate of gas is not going to have significant increases in efficiency, and you're just basically wasting money in doing this. So this is here, we're looking at TCE, contaminated groundwater, and we're stripping that to the air. Okay. Solubility plays a significant role. A chemical that is very soluble in water is going to be much more difficult to remove by air stripping. It doesn't want to leave that water. Temperature plays a role. The higher the temperature, the greater the vapor pressure. So the easier to remove it from a liquid into the air. We need good contact. I mentioned that in terms of the surface area. If we don't have good contact, we're not going to have good removal or good mass transfer. And you can think about this in terms of a river. If we're looking at the mass transfer of oxygen from the air back into the water, think of the red cedar. Is this mass transfer rate going to be more efficient in areas of the red cedar that are very quiescent, slow moving, or an area of the red cedar around the rapids behind the admin building? So where will we have a greater mass transfer, rate of mass transfer? Quiescent, slow moving region of the red cedar, or at the rapids by the admin building? By the admin building. Okay. It's more ability for the gas and the water to contact one another. And finally, the composition of the water and the wastewater. And we looked at this last Wednesday, so I won't go over this week. If you look at Wednesday's lecture, you'll see how to adjust your solubilities, your mass transfer efficient rates based on composition. So in terms of the types of processes that we're using, we can use spray towers. These are the most, the simplest of all of the processes. And you can see here it says air and particles. We can use this also for particulate removal, but we have a contaminated airstream shown here. And we're looking at clean water. And this is what's shown here. We're spraying that. We create these small droplets of water. The air moves through it, contacts the particles, and what do we end up? We end up with particles of water. So we end up with water containing the contaminated or the contaminant. And if we have particulates, and the particulates. So the way it's shown here, we start with a contaminated airstream. We end up with a contaminated water stream that we have to further treat. Now we can also do it the opposite way, where we start with contaminated water and we're ending now there. The mass transfer is to the air. They work reasonably well. They're useful for the more volatile gases, so they're not very efficient if we have gases that are not volatile. They have very low pressure drops, but the problem is they're really not that efficient. We're talking maybe 70 to 80% efficiency for most gases. We can move to tray towers, which are more efficient. So we're looking at improving that mass transfer and improving the contact between the gas and the liquid. Similar, again, we can either start with a contaminated gas or a contaminated water. We're looking at transferring that chemical to the other media where we then have to do further treatment. And as I mentioned, these are more efficient than your stripping tower. And finally, we can move to pack towers. These are the most efficient. And they're filled with typically this plastic media. You can see some of the examples here. Again, we need to have good distribution of the air into the water or the water into the air. You can think of it either way. And these we can achieve 99% removal of volatile organic chemicals. Typically, they range from about 5 to 12 meters in height. So they're quite high, typically permanently installed, although they can be on mobile units. The approach that we're taking, okay, is based on mass balance. So the way that I've written it here, okay, work through this, is we have, typically this is run in counter current flow. So we have water flowing down. It's more efficient to do it that way. And we have flow of water at the bottom. Okay, so we have a C in the water and a C out in the water. We have air. We have air flowing upward. Okay, so the counter current flow. Concentration of chemical in the air. So we'll denote that as A sub in, and flow out, A sub out. Okay, concentration leaving. We've written mass balances numerous times, okay, throughout the semester. So we have the rate of mass in equals the rate of mass out. Now, we're assuming here, and I'll explain this a little bit more in the next slide, but we have no reaction. So mass in equals mass out. And we can write that in more accurate terms. So we have the mass of water in. So let's go back. So we have that mass in. Okay. We have the mass of water out. And then we have the mass in the gas and the mass out in the gas. And as we've done numerous times this semester, we've then written this mathematically as the product of flow rate of water times the concentration of water plus the flow rate of air times the concentration in the air, and that equals flow out from the water and flow out in the air. Now, we're going to make several assumptions. Okay. One, we talked about an adsorption zone, we talk about an absorption zone. Okay. Within this absorption zone, we'll assume that there's complete mixing. So within this small parcel of air-water mixture, we have complete mixing. We'll assume, as I've mentioned before, that when we have dilute solutions, we can use Henry's law so that the concentration in the aqueous phase is equal to Henry's constant times the partial pressure in the gas phase. We will also assume that there are no changes in the volumes of the air and water. So as the air and water pass through this column, Q, volumetric Q, A in is equal to the volumetric Q, A out, and the same thing is true for the water. We will also assume that there's no accumulation in the reactor. Now that's different than adsorption, where we did have accumulation in the reactor. We'll assume that we have no reaction and we have constant flow rate of water and constant flow rate of the air. So this image is from the FE reference handbook. Type of question you may very well see on the FE, at least the environmental FE. You probably won't see it on the civil FE. In fact, the amount of environmental material on the civil FE has been significantly reduced. Major equations here are Henry's law, and note they use H here. And be very, very careful with the H, the Henry's constants. They vary significantly in terms of units. They can be dimensionless. They can be as written here, atmosphere meters cubed per kilomole. We have a number of equations here. Again, really what these here are all based on Henry's law. And we'll go through some of the terminology that's used here. Okay. Notice also that the concentrations are in kilomoles per meter cubed. Okay. So consistent with Henry's constant. And that's important to recognize that that's the case. So going back to the mass transfer equation. Okay. This approach, let's start with writing the mass transfer equation. So we have Q water times Cn plus Q air, concentration in the air, and this is in, equals Q W out, C out plus Q air, and the concentration in the air out. And remember, we said Q W in equals Q W out, and Q air in equals Q air out. So those were assumptions we've made. Now, we're going to make several other assumptions. We're going to assume that QWC out is much less than QA air out. Okay. Now, what we're assuming is roughly 100% transfer. What's important to recognize is that this equation here is transfer from the water to the air. The equation that we're using here, the approach that we're using, cannot be used for air to water. The assumptions are different. So because that, the approach can only be used from water to air. It's important to recognize that. We're also going to assume that Qn times air in is approximately equal to 0. So the mass of whatever chemical we're looking at in the incoming air is negligible. So if this is the case, then this term is approximately 0, and this term is approximately 0. So we can write our more general mass balance equation as QW Cn is equal to Q air times air out. Now we're assuming equilibrium at the interface. So this is equal to Q air times our Henry's constant times the equilibrium concentration. So it's this here, because their equilibrium concentration in the water, equilibrium with the air concentration. So with that, okay, and consistent, we use H prime. This means, okay, now we can write an expression that Cn divided by Cn star, that equilibrium concentration, is equal to H prime Q air over Q water. This term is referred to as the stripping factor. So in this approach, and this is the approach used in the FE reference handbook, uses this stripping factor. So it goes through basically to I've just derived the stripping factor, so you have a sense of where that comes from. So again, this is a screenshot from the FA reference handbook. We're using the same terminology that we've used before with adsorption. So we have the number of transfer units. Same as before, this is a measure of the difficulty of separation. And as was the case when we talked about adsorption processes, if we have one NTU, this is going to result in a change in composition equal to the driving force providing that change. And in this case, the driving force that is providing or causing that change is the difference between our equilibrium concentration and the actual concentration. Okay, so that is the driving force. The height of the transfer unit, analogous to what we've talked about before, this is a measure of the separation effectiveness. Notice here, we have KLA in the denominator. So the smaller the height of the transfer unit, the more efficient. So the more efficient the process. So we're going to do an example here where you're asked to determine the height of a packed tower, and we're reducing the amount of CO2. So it's prior to, for instance, a lime soda ash softening. We're removing CO2 from 60 milligrams per liter down to 10 milligrams per liter. You're given an operating temperature, a pressure. This is the dimensionless Henry's constant. You're given an air to water volumetric flow rate. So this is Q air to QW. Okay, and it's the volumetric flow rate. Now, notice, before we said this was in kilomoles per meter cubed, but yet we have a volumetric flow rate. Because PV equals nRT, the volumetric flow rate is equal to your flow rate in kilomoles per meter cubed. So we can use the volumetric flow rate ratio here. Can't use a mass flow rate because that's not the case, but we can use a volumetric flow rate. And you're given L. L is our liquid loading rate. And notice it's in per surface area of our column, and a mass transfer coefficient. And we're going to assume that the incoming air is free of CO2, or at least that CO2 concentration is negligible. We have CO2 in equals 60 milligrams per liter. This is in the water. We have CO2 out. That equals 10 milligrams per liter. Again, it's in the water. The dimensionless Henry's constant is given as 0.8317. QA over QW is equal to 160 to 1. L is equal to 0.4 kilomoles per second per meter squared. KLA is equal to 50 inverse hours, and A in, we'll say, is approximately equal to 0. Okay, so R sub S is equal to H prime over QA over QW. Notice by using H prime, takes into account the temperature, so it normalizes your Henry's constant as a function of temperature. And that is equal to 0.8317 times 160, 133. The number of transfer units is equal to RS over RS minus 1 ln of Cn minus C, divided Cn divided by C out, Rs minus 1 plus 1 divided by R sub S, and this is equal to 133 divided by 133 minus 1 ln. Now we can use, as we're dealing with CO2, the molecular weight is the same in or out concentration, so we can actually just use 60 over 10, 133 minus 1 plus 1 over 133. What we're really using here is the geometric mean of this driving force. Okay, so we're basically saying that the driving force changes and is best described by the this geometric mean. And this is equal to 1.8. Okay, so the number of transfer units is 1.8. That's our difficulty of separation. The height of the transfer unit is equal to L over M sub W. M sub W is the molar density of water times the mass transfer coefficient. And this is equal to, again, units are really important in this, 0.4 kilomoles per meter squared per second divided by 55.6 kilomoles per meter cubed. So that is the molar density of, and that's the molar density of liquid water, times our mass transfer coefficient. And notice, remember, that was in 1 over hours. We have our loading rate in inverse seconds, so we need to convert. Hours cancel, seconds cancel, kilomoles cancel. We're left with units of meters, 0.52 meters. Okay. And the height of our packed column is 1.8 times 0.52 or 0.93 meters. Okay, so we've determined the height of the column, which is what we sought. There's multiple other approaches, but gets much more complicated, but we'll leave it at that. And this provides you with some background information also that's helpful with the FE. So hopefully from this and from the previous lectures, you should be able to explain the process of absorption and also design an absorption tower.